We haven't really looked at how to determine those voltages, VL, VC, on those diagrams yet. So we've got our VL, VC, and VR, not forgetting that the current goes along with that one. How do we get those voltages? Well, we know that voltage is equal to current times resistance. That is Ohm's law, right? Now, what is the current in the circuit? Well, we said the current in the circuit is the same throughout the circuit and in phase with the voltage on the resistor. But we haven't figured out how to figure out these voltages yet. And that's because we need to know the resistance of the inductor and the resistance of the capacitor. Both of them have a form of resistance. So resistance for a capacitor, or inductor has a special word, and it's called reactance. And it is a form of resistance, but it doesn't generate heat. It has an effect on current flow, therefore we can say it's a type of resistance. But it doesn't generate heat and it doesn't use up energy. Okay, it's got a transfer of energy in the capacitor and the inductor. We know that as the magnetic field and the electrical field. So there's a special word for it. And so we have two formulas, one for the capacitor and one for the inductor. So the reactance for the capacitor, and the reactance symbol is this X. So we've got an XC and we've got an XL. The XC is equal to 1 over 2 pi FC. Now 2 pi F we know is omega, so you can write this like that. Reactance for the inductor is equal to 2 pi FL or omega L. Always when you see formulas, have a little think to yourself, what does that mean? That means that as the capacitor gets bigger, right, as the capacitor gets bigger, the reactance would get smaller given that you've got the same frequency. These are the things to look at, okay? So the smaller the capacitor, the bigger the reactance. These guys are fixed for a given frequency. They don't change for a given frequency. Alright? So that's the reactance for that component at that frequency. 2 pi FL. So as the inductor gets bigger, its reactance, which acts as a form of resistance, gets bigger. Alright? Now, impedance is like the sum of them all together. So impedance is the combined effect. And the symbol is this type of Z. But you can see these guys, the impedance or the reactance on the capacitor and inductor, sort of work against each other. So when we're working out those guys, we have to take into account that they work in an opposite sort of way. So if we're going to work them out all together, which we can, and we'll call that our Z, if you like. Let's just find it in my notes. Just make sure I do it all correctly. No, I've just got it down as a VS, that's okay. But Z is equal to XL minus XC squared plus R squared square root. So that's our formula for impedance. It's kind of like the total resistance. And if you want the current in the circuit, then you get Vs divided by Z equals the current. Now you should be looking at that and asking yourself, what's he talking about? Where's that funny light coming from? No, it's just coming from my light. It's just got to adjust. What we've got here is Vs divided by Z equals I. Great. But is that an IRMS or is that a VRMS? And the thing is, Z doesn't depend on an RMS or a peak value. So as long as, if you use peak, you're going to get peak current. Alright? If you use RMS, you're going to get an RMS current. So if you have Vs over I equals Z, it doesn't matter whether you use peak voltage and peak current, it will give you the impedance, or use RMS and RMS current, it will give you. But don't mix and match. The 2 pi will cancel, the square root of 2 will cancel out, so it doesn't matter which one you actually use. Now, the same can be said for when we're looking at working out those values again on our phasor diagram. VL, VC, VR. What are those values actually going to be? Now, we've said that X, L, X, C are the reactances. So we can actually work out, if we work out the, if we go V, L, divided by XL, then we should get the current. And likewise, if we do VC divided by VC divided by XC should give us the current. Remember, the current stays the same in the circuit. It's the same throughout. So I times XL equals VL, I times XC equals VC. So on the circuit here, again, you've got to ask yourself, are they talking about RMS or peak? Doesn't matter which, because again, the square root of 2 will cancel out. So if you use an RMS I, you're going to get an RMS voltage. If you use a peak I, you're going to get a peak voltage. Right? So on these phasor diagrams, if we divide each one of these guys, the V, by I, by I, by I, we're going to get, and as long as it's, again, we've got an RMS or a peak value, then we're going to get at those points XL, XC, and R. So sometimes you'll see the graph done that way. You'll get it done like this. And they'll call this XL, R, XC. Don't like it because really phasors represent quantities that are changing. And these guys are not changing. It just so happens that you can sort of add them up vectorially like this, but they're not really changing. The other thing that you'll notice sometimes, which I also don't like, is when you do this phasor diagram normally, and this is your VR, this is your VL, and this is your VC, these should be peak values because this is a phasor diagram. As these babies rotate, you're rotating their maximum amplitude. They give you the graph. They give you the peak values, they give you the zero values as they rotate. That's why we call them the phasors. So when people put them on a graph like that as an RMS value, I am very annoyed. But it will happen, and it will even happen in your tests. And the main thing you've always got to ask yourself is, what do they want? Okay, Mr. Stewart said it wasn't actually the best way to do things, but we know they do it that way, and all I'm trying to do is figure out what answers they want. So on these phasor diagrams, you will see, you should just have peak values, but you will see RMS values, and you will see just the reactances and resistances. Okay.